Good evening, class. We are looking at practice test number 3, module 3, covering chapters 5 and 6. Here, chapter 6, exponential and logarithmic functions. Exponential and logarithmic functions. In this example, we want to find the formula for an exponential function that passes through the points 0, 2000, 220, and it's in the form of f of x equals ab to the power of x. And recall that this base must be positive, and it can't be 1. Okay, so just reminding you that this b can't be 1, must be positive. So let's plug in the first pair. Remember, the y or f of x are the same thing. So this gives us f of 0 is a times b to the power of 0 is 2000, and the second one, f of 2, ab squared is 20. So when we look at this one, this is 1, so a becomes 2000. So if a is 2000, I'm going to replace it here. So f of x has the formula 2000 b to the power of x. So 2000 b squared must be 20. So this is the general formula, or specifically, let's plug it in here. And now, if we divide by 2000, both sides, okay, we get b squared equals 1 over 100. B is 1 over 10. By the way, b is plus minus 1 over 10. There are two answers, but remember, b must be positive. There are two answers. And so we just choose the positive. In other words, you can write plus minus and then say b is only positive 1 over 10. Okay, you can do that, and therefore here's the formula, everybody. Pretty straightforward. This deposits $10,250 into an account that earns 4% compounded interest. How much will the account have at the end of 10 years if it is compounded monthly, and so forth? So first, here's the general formula for compounding. A equals P times 1 plus R over N to the power of NT. P is the principal, R is the rate, N is the number of compounding that takes place per year. So when we say yearly, N is 1. When we say monthly, N becomes 12, and so forth. Okay, so at this point, let's plug in everything that we have. For example, we know R is 4%, we know P is 1250, and we know T is 10. So let's plug in and make that general. Now, more specifically, now we're going to look at monthly. So this is in general. So here's the principal, here's the rate, 4% is 0.04, and here's the T, which is 10. Now we're going to replace the N with, in the case of a monthly, N is 10. My apologies, 12. So let's replace the N with 12. So obviously this is 120. You do the math, you put it into a calculator, it results in $15,281.03. When it comes to rounding for money, we go with 2 decimals, which means we look at the third one and we make a decision on the second. Same question, but this time it's getting compounded weekly. So when we go back to this equation, everybody, weekly N will be 52. N will be 52. Let's plug in. And again, you just put it into a calculator. You divide 0.04 by 52 plus 1 to the power of 520 times 10 to 50, and gives you a little bit more, $15,288.85. So as we add to n, as n becomes larger, the amount gets larger. So because it takes weekly compounding now. Now, how much will the account have at the end of 10 years? If it's compounded continuously, it becomes A of t equals P e to the power of RT. I hope everybody remembers this formula. So basically, we have the same situation, A of 10. So T is 10, P is the same principal of $10,250, or is the same rate of 4% or 0.04, and T, same 10 years. And of course, this would be 0.4 e to the power of 0.4 times 10,250 gives us $15,291.20. As you can see, this is larger than that because it's compounded indefinitely. Now, I want to remind you of this concept. When the continuous compounding happens, there is something called doubling. And simply put, doubling time refers to the time it takes the principal to double up. So in order for that to find out in general, you don't even have to know this number, by the way. Okay, that's very interesting. So instead of using $10,250, I'm going to leave it as P. But if it's doubling, this becomes 2 times P, everybody. So I can drop the P, 2 is e to the power of RT. And now if I take the natural log of both sides, if I take the natural log of 2 and natural log of e to the power of RT, I hope you know the formula then becomes RT, right? And therefore, since we want the time, we divide ln2 by R, and R is 0.04, and it gives us 17 years, a little bit longer than that takes for it to double up. Use graphs shown to answer the following questions. All have the format of f of x equals ab to the power of x. Which graph has the largest value of b? Which graph has the smallest value for b? I want to remind you of a couple of things. So y equals a to the power of x. The base is a, b, c, you name it. It has to be larger than 1 if it looks like that. And if it looks like that, this is an exponential growth. For the exponential decay, it's between 0 and 1. And again, remember, a cannot be 1. So let me remind you that a, in this case, the base, okay? We're referring to the base, cannot be 1. And so with that being the case, for example, if this is 2 to the power of x, this is 2 to the power of minus x, okay? Or 1/2 to the power of x. This is another way of writing it, everybody. We could write this as 1/2 to the power of x. The reason is because 2 to the power of -1 is 1/2, and that means the number. If a is larger than 1, exponential growth. If it's less than 1, in this case is 1/2, it's exponential decay. Okay. So this is showing that as the base gets larger, 2 then changes to 5, the graph gets closer and closer to the y-axis on the right side as it gets larger and larger. By that we mean the base is larger than 1 to begin with. The base is between 0 and 1, so it's an exponential decay. And this is another one. This is a general case. This one, since the base is b, and then we are multiplying it by a. This one has coordinates 0, a, okay? Whereas here it has 0, 1, 0, 1, 0, 1 as the y-intercept. So that's important to see that, everybody. So this is 0, 1, but this is 0, a. Why is this 0, 1? Because in front of the base there is nothing. In this case, in front of the base is a, okay? All right. Maybe we should actually stick with the same base, so that maybe I change that I make later on. But in any event, I hope the concept is clear. So let's go back and answer this question. It's asking which graph gives us the largest value, okay, for a b. Well, the one that is closest to the y-axis on the right side, we discussed that, okay? So look at these two, for example. So on the right side, we have this one and this one and this one. So D is the closest one to the y-axis. So there are three of them, right? So the answer is D. Now, which one has the smallest value for B? Okay. Now, the closest to the y-axis on the left. Okay. So on the left, we have this one and this one and this one. And so this is the closest to the y-axis. So graph C. Which graph has the largest value for A, and which graph has the smallest value for A? So in other words, remember all of this, 0A, 0A is your y-intercept. Okay, 0A is the y-intercept. So if you look at the y values here and here and here and here, this one has the largest y value. So graph C. Take a look. Now, on the other hand, for this one, we want the smallest one. So this is smaller, this is smaller, this is the smallest. That would be the graph F. So I hope it's clear to everybody, okay? Use transformations of the graph of f of x equals to the power of x of the function below. State the horizontal asymptote, domain, range, you name it. Well, first of all, 2 to the power of x is the regular one, 2 to the power of minus x. You reflect it across the y-axis. So 2 to the power of x is what you know. Okay, and by the way, it may or may not even be to scale. It doesn't matter. With this one having coordinates 0, 1. And so 2 to the power of minus x reflected with respect to the y-axis, looking like that. We have the equation y equals 2 to the power minus x, and the y-intercept of 0, 1 doesn't change. So when you look at this graph, you can even put them next to each other. You notice that the horizontal asymptote is the same as the horizontal asymptote, which is the x-axis of y equal to 0. The domain here and here don't change. Negative to positive infinity. The range doesn't change, 0 to infinity. So what has changed? This was increasing, but this is an increasing function, but this is a decreasing function. So g of x is 2 to the power of x plus 1. How about this one we want to graph now? Now that's the same as this guy, but it's been shifted up by 1. So when it goes up by 1, the 0, 1 goes to 0, 2, and this x-axis or y equal to 0 becomes y equals 1. So your y-intercept was 0, 1, but it's now 0, 2. So that has changed. And your horizontal asymptote was the x-axis, or y equal to 0 is now y equals 1. So what is the effect of that? Horizontal asymptote has changed. What about the domain? The domain hasn't changed, the same x values. But the range over here or over here was from 0 to infinity, but now it's from 1 to infinity. The range has changed, everybody. The range has changed. Okay. The function to the power of x plus 1 shifts us up by 1, and therefore it has an effect on the range and the horizontal asymptote. All right. Here's the function. Consider the function f of x equals 4 to the power of x. Write a function that results from the given in formation. So we are going to take this up by 3 units. So add 3. Now shift f of x 5 units left. That means not this one. Go back to the original one. Shift f of x 5 units left. So change the x to x plus 5. So 4 to the power of x plus 5. Reflect f of x about the x-axis. Since it's about the x-axis, just put a negative sign in front of that, and the y in essence. Remember, 4 to the power of x represents a y. But if we want to reflect it about the y-axis, put a negative sign in front of x. Okay. The graph to the right is transformation of f of x equals to the power of x. Write an equation for the graph shown. Well, let's see what we have here. That's some sort of a exponential function with the horizontal asymptote being now different. So this is 2 to the power of x. That's what we begin with because they said so. So this is some sort of a transformation of that. There seems to be a transformation of 0, 1. And of course, now it has been 0, 2, but it's been reflected also. So if we reflect it across the x-axis, looks similar to that. So minus 2 to the power of x. So what is this location now? 0, negative 1. But we want to take it to 0, comma 2. This has coordinates 0, comma 2. So we want to take this up to 0, comma 2. We have to shift it up by 3 units. This is y equals 3. It's been shifted up by 3 units. This is 0, 2. Very straightforward, everybody. Y equals 3. So f of x is minus 2 to the power of x plus 3. That would be the graph. Okay, everyone? So this is the graph of f of x equals minus 2 to the power of x plus 3. All right, logs. Let's remind everybody of logs, what we learned in intermediate algebra. The relationship between the two, if we can go from one format to the next, we are fine. In other words, take a look at this. Log x base b or log x to the base b equals y. Now look at the arrow that I put in here. B to the power of y equals x. If we can make this transition from here to here, we never have any problem. Back and forth, of course. So the base b must be positive, larger than 0. Cannot be 1 either, 1 to a number, 1 to a power, any power is 1. So y equals log x base b is equivalent to x equals b to the power y. So pay attention to this and the arrow, it will make perfect sense. Now, we have these rules. I hope you remember them. So let me quickly recap for you. When y equals log x base b, it's the same as b to the power of y equals x. That's a general form, meaning the base can be any number as long as it's a positive number and it's not 1. If you look at this arrow, b to the power of 0 is 1. B to the power of 1 is b. B to the power of x is b to the power of x. Now this one, we've proved it in previous courses. You can look at the proof in my notes also. These two together refer to the fact that logs and exponential functions are inverse functions. They undo each other. Log of xy is log x plus log y, as long as we have the same base, b. Log of x over y is log x minus log y, as long as they have the same base, b. Log of x to the power of n is n log x, so as long as they have the same base. This is the product rule, this is the quotient rule, this is the power rule. Now, if you're comfortable with that, then when we go to natural logs, where the base is e, remember when we say y equals ln x e to the power of y equals x, that's the same thing. We write ln and no base, that means the base is e. Transition from here to here should be easy. I hope it is easy. So ln 1 is 0, ln e is 1, ln e to the power of x is x, and the rest of it. E to the power of ln x is x. So these two, again, just like these two, okay? Refer to the fact that logs and exponentials undo each other, then we have the product rule, the quotient rule, the power rule. If the base is 10, so when we write log without the base is 10, so y equals log x is the same as log x base 10. We don't write the 10, okay? So 10 to the power of y is x. And again, the same properties, but for a common log. Log 1 is 0, log 10 is 1. Remember, these two must be identical. When we don't have a base, the base is 10, right? Log 10 is 1, log 10 to the power of x is x, 10 to the power of log x is x, and these three, the product rule, quotient rule, and the power rule. If you look at this graph, it represents the fact that exponential functions and logarithmic functions are inverse of each other. Therefore, they are symmetric with respect to the line y equals x. And here's the change of base formula. Log x with base b is the same as log x over log b, as long as we choose some base, such as a. Obviously, we either choose common log or natural log, because that's what most calculators can handle, but not a general case. So let's quickly see what we get here. Five to the power of q is m, and we don't have anything, but we have ln, that means e to the power of z is v, and when we don't have anything, but we have log, that means 10 to the power of t is w. So it's a very simple case. Now we want to go back 3 to the power of x is y. That means log of y with base 3 must be x. This e to the power of k equals h. So ln h is k, 100 to the power of a is b, log b base 100 is a. So in short, it's just going back and forth here, everybody. We should have no problem with that. Okay. Doesn't matter, it's a general case, it's a natural log, or it's a common log, it's fine. State the domain, vertical asymptote, and the end behavior of the function. Now, exponential functions, generally speaking, they give us horizontal asymptotes. Logarithmic functions in general, they give us vertical asymptotes. So log x has a basic graph. Let me just remind you. Again, obviously, this is not to scale. So this is the graph of y equals log x base a, where a is larger than 1, okay? And this is y equals log x base a, where a is between 0 and 1, okay? And in both cases, the y-axis, or x equals 0, is the vertical asymptote. So where we have x minus 7, it's been shifted to the right by 7 units. So this one has been shifted to the right by 7 units. And remember, this point has coordinates 1, 0. Now we move it by 7, becomes 8, 0. 1, 0, and now 8, 0. So let me erase my mess. Here's the graph. Here's your vertical asymptote. And that's x equals 7. Okay, this is, as I said, 8, 0. This is x equals 7. In general, one easy way to find this, if you set this equal to 0, this is your vertical asymptote. By the way, the basic log, this one, the domain is from 0 to infinity. 0 is not included. Range is all real numbers. It's, remember, it's the inverse function with respect to exponential functions. So domain is 7 to infinity. Range is all real numbers, negative to positive infinity. The range hasn't changed, but the domain has changed from 0 to infinity now to 7 to infinity. And the end behavior is as x goes to 7, as x goes to 7, f of x goes down to negative infinity. In this case, as x goes to 0, it goes to negative infinity. And as x goes to infinity in both cases, y goes to infinity also. All right, we're going to do the same thing. We're going to state the domain, vertical asymptote, and the end behavior of this function, ln of 2 minus x. And by the way, very easily, you can see 2 minus x equal to 0, x equals 2 becomes a vertical asymptote. But what is the transformation? First, let's start with ln x, and then we are going to go with ln of negative x. And that means the negative sign is in front of x, the transformation, that means reflected across the y-axis. So this is y equals ln x, with this point having coordinates 1, 0. This is y equals ln of minus x, is the reflection of that, and that has coordinates, the x-intercept has coordinates minus 1, 0. By the way, there is no y-intercept. Okay. All right. So what happens now, we want to go from this to this one. So we need to add 2, or we can say minus x minus 2. It's important to have it in this format because now it becomes clear that this guy shifts to the right by 2 units. Shifts to the right by 2 units. This is the proper way of writing it. So here's y equals ln x, here's y equals ln of minus x, and here's the one that we have, and this is identical to, by the way, 2 minus x. And I can't emphasize this enough. The methodology is to put the negative in front of x, and then put this in a parenthesis so you know it's shift to the right, which means now again, 1, 0 went to minus 1, 0, and then back to 1, 0, but it's a different graph, and it looks like this with this vertical asymptote. Again, an easy way to find that. You said 2 minus x is 0, so x equals 2. That's your vertical asymptote. Okay, so this is 1, 0. This is your vertical asymptote, and the domain from negative infinity to 2, it stops at 2. The range hasn't changed, is all real numbers. As far as the end behavior is concerned, when x goes to negative infinity, y goes to positive infinity. That means g of x. When x goes to this number 2, then y goes to negative infinity. So that would be the end behavior, everybody. So transformation. State the domain, vertical asymptote, and the end behavior of this function. H of x is minus log of 3x minus 4 plus 3. And we are going to start with, of course, log x, and then log of 3x. That is the very first one we want to start. So as x changes to 3x, there is a horizontal shrinking by a factor of 3. Okay, so what happens when you have a basic log x, it shrinks by a factor of 3. So if the x intercept is located at 1, 0, now it shrinks by 1/3, becomes 1/3 comma 0. So please understand, this is 1, 0. This is the basic log, or log x. This is y equals log x. And the blue one, the top one, is y equals log 3x, and that's y, 1/3 comma 0. So we want to make it look like this. So first, you have to understand this is the same as 3 times what? X minus 4/3. And therefore, because x is replaced by x minus 4/3, it shifts to the right by 4/3. So we have this one, and now this is the one we are dealing with. That means 1/3 comma 0 goes to the right by 4/3. So you're going to add 4/3 to 1/3, becomes 5/3. So the red one is the original log x. The blue one is what we had here, log 3x. And the green one has been shifted to the right by 4/3. We're almost there. We have a couple more steps. Negative in front of the function. If I put a negative in front of the function, this last one, this green one, will flip over with respect to the x-axis. So I put a negative in front of it. It flips over. Okay, it reflects across the x-axis. So this green one now becomes this purple one. Now let's go back to here. Everything is done except +3. So that means move it up by 3 units. So now the +3. So that is that hasn't changed as far as the location of the x-intercept. It just flips over, but it remains as 5/3, 0. So that doesn't change. Now we're going to shift it up by 3 units. So the same thing. Look at this last one now. Okay, this purple one goes up by 3 units. So this purple one, it went up by 3 units. And so the x-intercept, which had the coordinates 5/3, 0, 5/3, 0, okay, now has gone up to 5/3, 3. X equal 4/3, I want you to know that to get this, I mean, if in case you don't see it from here, 3x minus 4 equals 0, x equals 4/3. That's how you get that. Now, pay attention to this. This is, everybody, the original 5/3, 0 has been shifted to 5/3, 3. So I want you to see that, okay? That is extremely important. Now let's discuss the domain and range. Well, because the vertical asymptote has the equation 4/3, so the domain is from 4/3 to infinity. But there is no limit as far as the range. The range hasn't changed. It's all real numbers. So the end behavior says when x goes to this number, 4/3, okay, the function blows up to infinity. But if x goes to infinity, then the function goes to negative infinity. All right, expand each log. Assuming we are comfortable with properties of logs and it becomes easy to do so. This is simply using this property, so it becomes log of x plus log of y plus log of z. All of them have the same base 7. This one is going to use the quotient rule, ln 9 minus ln x. This one, you put the 10 in front, you're following the power rule. Put the 10 in front. 10 log 1. And this one, you can do it in one shot, but if you wanted to do it in a couple of shots, we are going to write log of the top, of course, same base. The base is x, a squared, b to the power of 4 minus log of the bottom. And again, to the same base, x. Now, this one, we can write it as log a squared base x plus log e to the power of 4 base x. This one, the 2 sits in front. This one, the 4 comes to the front. This one, the 7 comes to the front. And the final answer is 2 log a base x plus 4 log b base x minus 7 log c base x. Same base. We're going to continue with the rules. Well, we are going to write this to the power of 1/2 because it's a square root. If it's a cube root, 1/3. If it's the fourth root, 1/4. And then we're going to put the 1/2 in front. Okay. So we're going to have 1/2 log of x cubed with the plus log of y to the power of 5. They all have the same base, namely 10. So this 3 comes in front, this 5 comes in front. And with 1/2, they become 3/2 and 5/2. So this one is 3 in front, 3/2 log x. This one is 5 in front with 1/2, 5/2 log y. Part B is very straightforward. We are using the quotient rule, ln of the top minus ln of the bottom, and nothing can be done to the bottom. It's just done. We can do this in one shot if you have enough practice, or we can do it in 2 shots, log of the top minus log of the bottom. Now, the top, we can write this as x to the power of 1/2, and this one 1/3. So we have log base 4 of x to the power of 1/2 plus log base 4 of 10y to the power of 1/3 for those two. So what happens, this one 1/2 sits in front. This one 1/3 sits in front. Log of 10y is log of 10 plus log of y, and this one 10 sits in front. So please understand that this is this part, okay? So we are expanding. It's very straightforward. Now we want to bring him back. In other words, we are going to go from, we went from left to right. Now we're going to go from right to left. So we're going to combine them by multiplying this. So this becomes log of 2x to the power of 4 times 3x to the power of 5. So when you multiply them, you get log of 6x to the power of 9. And this is the ln of 6x to the power of 9 over x squared, which becomes 6x to the power of 7. This one, I'm going to get rid of the 2 and put it here. This one, I'm going to put the 3 up here. And now this becomes log of x squared times x plus 1 cubed. Now, depending on what they ask you, as far as I'm concerned, this is a done deal and it's perfect. They may want you to multiply this. I don't, so it's up to you. All right. Again, this can be done in one shot. Anything that has a plus sign goes to the top. Anything that has a negative sign goes to the bottom. But in any event, we can do the following. First and foremost, I'm going to get rid of the 1/2 and put it here. Get rid of the 3 and put it here. Okay. Then I have this one and this one, which makes it log of x times z cubed minus log of y to the power of 1/2. Y to the power of 1/2 or square root of y. And that uses the quotient rule. So log of this over the square root of y. That's your final answer. So you should be able to go back and forth. It's really not that big of a deal. We want to solve this. If you're dealing with the exponentials, a to the power of x equals a to the power of y refers to the fact that x and y, the exponents must be the same. If a to the power of x and b to the power of x are the same, then the base a and b must be, the bases a and b must be the same, okay? So in this case, the base are the same, therefore the exponents must be the same. And if I move things around, and divide by 3, x becomes -1. If you look at part B, since this one has base 4, and you can write this one as 4 cubed and this one as 4 squared, you can. However, if it can't be done, but you can use, for example, base 2, you can do that. For example, instead of 16, if I had 8, I had to go with 2 cubed. If I had 8, I had to go with 2 cubed, so I can change even this 4 to 2, okay? That means 2 squared. All right, so now, as you know, the left side is 4 to the power of 3 plus 3x, so 3 plus 3x must be equal to 2. We're going to subtract the 3, and we get 3x equals -1, so x is -1. 2e to the power of 3x is 13. Let's divide both sides by 2. And let's take the natural log of both sides. So the left side becomes 3x. So x is the right side divided by 3, or 1/3 of the right side. Now, please understand, this is the exact answer, and most of the time we want that, whereas 0.62393 is an approximation, and if they ask you for the approximation, you have to use the proper number of decimals. You could use substitution, or you may recognize that if you treat this as a simple factor and you want two numbers, the product is c, which is -6, and the sum is b, which is -1. Those are -3 and 2. This is how you write it. However, the substitution, you let e to the power of x be anything except x. Let's say y. Now you have a y squared minus y minus 6 equal to 0. And you're going to go with y minus 3 times y plus 2 equals 0. And then you go. It's up to you. It depends how easy you find it. And so we have either e to the power of x equals 3 or -2. This can't be. As you know, exponential functions have a range of 0 to infinity. They can never be 0 either. So if e to the power of x is equal to 0 or a negative number, there is no solution. But the other one, we can take the natural log. The left side becomes x, and the right side is ln 3. And again, this is what we really want, the exact answer, okay? This is an approximation. Most of the time, we are not interested in that. It's important to know the basic definition. So look at the arrow again. 3 squared is 9k. We know 3 squared to be 9, so I can drop this, and k becomes 1. We use the product rule, the reverse process, and we multiply these two. So anytime you have a bunch of logs and a number, you bring all the logs to the one side, number to the other side, and then you go by the definition. This is log of negative 20x. Maybe we should put it in brackets like that. And here's the arrow. Of course, the base is missing. That means the base is 10. As you know, the 10 squared is 100. And if you divide by negative 20, x becomes negative 5. Now, this is extremely important to check because basic log has a domain of 0 to infinity. If you put the negative 5 here, makes this positive 25, and that's fine. Okay, it checks, it does work. Well, in this case, they both have the base 7. So 5n minus 2 is 8 minus 5n. N is 10, and n becomes 1. In part J, all of them involve logs. When everything is log and nothing else, you don't have to move things around. So you have to combine each side into a single log. So in this case, you have to multiply these two. Now, each one has a single log. They both have the same base. Therefore, they must have the same argument. These two must be identical. Please understand, it's not that we drop the log. We are saying both logs are equal. They both have the same base. They must have the same argument. And now we move the x. We divide by 11, and we're done. The answer is x equals 12 over 11. All right. Since part A involves all natural logs, we don't have to move anything. We are going to put this together by writing the quotient through the reverse process, ln of x plus 4 over x. The right side doesn't change. They have the same base, namely e. They must have the same arguments. These two must be identical. And to solve this, we do the cross product. I put a 1 here. This times this, and this times this. So we have x plus 4 equals x squared plus x. Again, we don't have to move anything. We just drop the common x on each side. X squared becomes 4. And x has two answers, positive, negative 2. We go back to the original function, original equation. If we put minus 2 here, minus 2 plus 4 is positive 2 is fine. But minus 2 is not fine here. So therefore, I don't even have to check with this one. It's out. We have a number on the other side. So we bring all the logs together into a single log as log of x times x minus 1. And now we go with the definition. So x times x minus 1 is 2 to the power of 1. This is obviously x squared minus x. And we're going to move the 2, becomes minus 2. It's a very simple case of a factoring. You want two numbers, the product is negative 2, and the sum is negative 1. The answers are negative 2 and positive 1. So we have two answers, either x is 2 or negative 1. Go back to the original one. 2 works here. 2 minus 1 is 1 is works. Negative 1 doesn't work here. You don't have to check here. Doesn't work here, you don't have to bother anymore, it's out. Okay. Again, why is it that it doesn't work? You can't have a negative argument. The argument must be larger than zero, must be positive. It can't even be zero for any logs, regardless of the base. All right, we want to move this 10 to the other side to solve for the power of x plus 10 equals 3. And we get 4 to the power of x equals minus 7. Any exponential function, regardless of the base, can't be negative, can't even be zero. No solutions. For part B, one easy way is the moment you see number 1, remember, if you pick a base to the power of 0, you get 1. For example, 2 to the power of 0 is 1, 5 to the power of 0 is 1, and so on. Because this is base 7, I'm going to choose 7 to the power of 0. And therefore, their exponents must be the same, meaning x minus 10 must be 0, and it makes x 10. And you can, of course, check, and you're done. Now, we are looking at the situation where the base on the left and the base on the right are different. The exponents are also different. Then what do? These are a little bit more difficult than what we have been doing. We are solving for x, which happen to be an exponent. We take a log of both sides. Now, with regard to what base? You can take a common log or a natural log. You can, in some case, if any of them is e, let's say if this was e, we would take a natural log. If this was 10, we would take a common log. But now, since we don't have a 10 or e, we just take either one. So take a natural log of both sides. So this x sits in front, this x minus 2 sits in front. Remember, you're solving for x. So I'm going to distribute the natural log. And please understand that ln 9 or ln 4 is not missing. None of them is missing. They are exact answers. Since I'm solving for x, I'm going to move this one to this side. And now I'm going to factor the x out. And now I'm going to divide by the parentheses. So minus 2 ln 9 is over ln 4 minus ln 9. This is an exact answer. I also want to show you if I put the negative, okay, down here, it becomes the same as 2 ln 9 over ln 9 minus ln 4, in case you see that they are the same class. These two are the same. Now, if they ask for approximation, you can put this in a calculator. What you're looking at, both cases are exact answers. Okay, both cases are exact answers. And that is extremely important to understand. Let's assume log 2 with some base. We don't have the base. B is A, log 3 with the same base is B, log 5 with the same base B is C. We want to evaluate those. So log of 50 base B, I hope you recognize, you have to use factoring to get to 2 and 5. So this is 2 times 25 or 2 times 5 squared. And I remind you, in case you want to do that from the scratch, I do that to 300. I'll show you how you do the factoring. So this is log 2 plus 2 log 5. Okay, log 2 plus log of 5 squared, or 2 log 5. So log 2 base B is A. Log 5 base B is C. So this is A plus 2C. First and foremost, this one is 300 to the power of 1/5. and it makes it 1/5 log of 300 base b. But this 300, I want to show you quickly and remind you about elementary algebra or basic math. I want to factor this, and remember the prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and you continue. So you start with the first and smallest prime number. We know it's divisible by 2 because it ends with 0. We do it again 2, and then this is no longer divisible by 2. 7 and 5, they add up to 12, so divisible by 3. We get 25. Not divisible by 3 anymore, so 5. We get 5, 5, we get 1, and so it's 2 squared times 3 times 5 squared. So that means this is 1/5 of log of this plus log of this plus log of this. This one gives you 2 log 2. This one gives you log 3. This one gives you 2 log 5. All of them the same base, namely b. As you know, this is a, this is b, this is c. So we have 1/5 times 2a plus 1b plus 2c. Very straightforward, everybody. I want to look at the last question in case. A nuclear reactor contains 200 grams of radioactive plutonium at 239p. Plutonium decays according to formula equals a sub 0 e to the power of negative 0.0000284 t. How much will remain after 5,000 years? Find the half-life of plutonium. And by the way, the exponential growth, you remember that now? This is in essence the exponential decay. That's why we have the negative signs like n of t equals n sub 0 e to the power minus kt. So what happens is that the initial amount is 200 grams and t is 5,000. So basically now this one, you replace it with 200 and t with 5,000. So the first part is elementary. So again, 200 because that's a sub 0 and 5,000 here. So you multiply these two numbers, you raise e to that power, you multiply it by 200. And after 5,000 years, 200 grams goes to 173.52 grams. Okay. So the question is, what is the half-life? That means how long does it take for the amount of plutonium to go to half of its original size? Of course, the amount is given as 200, but regardless of that, we can work on the general formula and work it out because we really don't need to know the initial amount. Rather, if we go with this formula, this is the initial amount. Now we want half of that, half of a sub 0. And as you can see, these two cancel each other. And now if I take the natural log of both sides, the left side is ln1 minus ln2, and the right side, just the exponent comes down. And as you know, ln1 is 0. So you divide both sides by this number, negative 0.000028284. And now if you put it into a calculator, by the way, negative over negative is positive, it gives you the following, which is 24,406.59 years. In this case, because even this formula is somewhat an approximation, what they do is they probably want it closest to the nearest whole number. But whatever they ask you as far as the rounding is concerned, and what I want you to note is that the continuous rate of growth is R, or 0.0000284 in this case. That is called, as far as the rate of growth is concerned. Okay, class, that's it.